Okay, let's start. Hello and welcome everyone. My name is Srdja, and I was responsible for the technical aspects of our new game, Spellsouls Duel of Legends, and this also includes all of its graphics. Before we officially start, please put your phones on silent. And a little bit about Nordeus and the game itself. So Nordeus is an independent mobile game developer based in Belgrade, Serbia. Our flagship game is Top 11, the most popular mobile sports game in the world, with over 180 million registered users. We're currently developing Spellsouls, a 1v1 PvP battle game, and it's currently in soft launch in multiple territories, and hopefully it will be full launched later on this year. Since you probably haven't had a chance to see it yet, we have prepared a short gameplay video so you can see how it looks like. From a technical standpoint, we had two big things that we wanted to achieve. The first one is that we wanted to create a AAA experience on mobile. Usually in our industry, when you say AAA experience, you mean big production or marketing budgets, but we actually use it to mean best-in-class user experience. We want our game to feel amazing to play. And in the realm of graphics, that means that it needs to look amazing, and it also needs to run extremely smoothly. And because of that, we actually want to run our game at 60 FPS on as many devices as possible, which is no small feat on mobiles, especially with such a heavily graphical game. But in contrast to that, we also want our game to be played by as many people as possible. So we want to support a very wide range of devices. We currently support iPhone 4S, which is going to be almost 7 years old soon. And those two goals are in stark contrast with each other and required a lot of effort to achieve. So we encountered a lot of different challenges doing this game, and we'll be talking today about 4 big topics. The first topic is our general rendering, which is using PBR shading. Secondly, our spells are pretty much pure VFX, and we needed a very good VFX shading system for that. We also have a lot of units on the screen at the same time, much more than you could actually see in the video. And we required a very fast way to skin and animate all of them. And finally, probably the biggest challenge out of them all is optimizing to 60 FPS. We'll share a lot of different techniques that we used in all of these areas, so you can use them to improve your own games. Now then, let's start with PBR shading first. You might be wondering why did we even go with PBR on mobile, since it's usually not such a good fit, especially from a performance standpoint. Well, our game has a semi-realistic, dark fantasy kind of art style. And we also have many different arenas, as you could see in the gameplay video, all the way from tombs inside of a mountain to palaces in the sky. And those two things lend themselves very well to PBR shading, so we wanted to give it a go. Usually when you start doing PBR shading, you will use the standard PC approach. You will use the GGX lighting model. But that approach is actually really expensive, especially on mobiles. So you won't be able to run your game at 60. You might not even be able to run it at 30 on most devices. Only the high-end ones will actually work. So we did a lot of research there, and we went kind of old school. We ended up using the normalized blind foam lighting model. This is something that gave us a really good balance between graphical quality and performance. And if you're looking to do PBR on mobile, I highly suggest that you start with this and not GGX like we did. These are some of the materials that our artists used to test our shader. Since we're developing a fantasy game, there are certain materials that are much more prevalent. We have a lot of metals, we have stone, we have wood, we have leather. And you can see that all of those materials actually look pretty nice under our shading. But there are certain materials that we simply don't need in our game. Nobody uses plastics in a fantasy world. And the plastic here is the red ball. You can see that it's not perfect at all. If you had a lot of plastics in a game, you wouldn't want them to look like this. But it's fine for us because we don't actually need them. So one key point that I want to make throughout this entire presentation is that it's worth it to start with a generalized technique like the standard normalized blind foam model, but specialize it for your use case, especially on a performance-constrained platform such as a mobile device. No. So when we're talking PBR, we have to have a texture that's going to describe how our material works. The most standard way to do this is to have roughness and metalness in it, and we use those two parameters in a pretty standard way. The problem that we first encounter when doing PBR is that PBR requires a lot of computations in your shaders. And your game is very likely going to end up being computationally bound. So ideally, you want to reduce the instructions in your shader as much as possible. And in the core of the PBR shader, we noticed that a lot of instructions were going on calculating how much to sample and how strong the reflection from the environment reflection probe should be. So we decided to, I should actually say that we actually had a lot of free bandwidth remaining. We were just computationally bound. Bandwidth was OK. So we actually decided to put another parameter in our material parameters texture. We call it reflectivity. And it describes how much of the environment should be reflected back on certain parts of our character. This is a really good thing to do if you're computationally bound on mobile. Since we only added an additional channel to our texture, fetching it back is pretty much free. But this is not actually a catch-all solution, because on mobiles, you might as well end up being bandwidth bound. And in that case, you might actually consider doing the opposite approach, moving things from textures into calculations inside of a shader. We ended up having a lot of free bandwidth because we don't actually use post-processing except on the very highest end of devices. We found that the overall game quality was better if we got the game to run smoother than if we added some post-processing into it. And for a normalized blind foam lighting model, we did a lot of iterations with our artists on that one. It started with a completely standard normalized blind foam that you can find anywhere on the internet, and ended up looking like this. This is the exact formula that we use in our shader. If you ever did any normalized blind foam work, you'll notice that the formula is not exact, but we're still making a fantasy game, so we need to tweak some things so that our artists could get the look that they wanted. And how does this all come together? Well, this is our character with just the diffuse applied. You will notice that there's still some ambient occlusion in there. Since we're developing for mobile, we cannot use screen space ambient occlusion, so we baked a little bit of occlusion into the albedo of the texture. Next up, we apply our environment map. You can notice in the gem in the middle, for example, how it's much more shiny now and all of the metals on the pauldrons. Next, we apply our normalized blind foam spectral lighting, and we also have a kind of pseudo light that's providing rim lighting for a character so they could pop out of the background even more. And this is how it looks in motion. So that's pretty much the secret sauce for our PBR shading. But it's not the only technique that we needed to get the game looking as good as it does. And for PBR shading especially, you absolutely need to do all of your calculations in linear color space. It's necessary, because if you don't do it that way, you're going to end up with incorrect results when outputting the light from the shader. The problem on mobiles is that only about 50% of devices actually support linear color spacing hardware. And on PCs, pretty much all of the devices support it. And we want to run the same shading on all of the devices, and we don't want to limit our player base to only 50%. So we needed a way to solve it. And the main problem here is that when you're fetching pixels in the shader from a texture, the colors that you fetch will be in gamma 2.2 color space. And you need them to be in linear. The way to do this is to actually, whenever you fetch the pixel, raise it to the power of 2.2. But you're very likely going to have a lot of different texture fetches in your shader. In our case, we have between 5 and 6 in most cases. And that's going to get pretty expensive pretty fast. We're losing about 20% of performance doing power functions inside of a shader that much. So we needed another way to solve this, and we got to thinking. And the first idea that popped into our mind was, why don't we pre-correct the textures so that when they're fetched in the pixel shader, they're going to end up in linear color space. You can see on the left the actual texture, how it looks normally with gamma 2.2. And on the right, you can see the texture with gamma 1. That one will end up being correct when fetched in the shader. But even on this projector, you should be able to see the problem. We actually lost a lot of color information in the dark shades. The thing is that textures don't have infinite precision. We only have 8 bits per channel. So all of the dark colors get crushed together, and the darker the color is, the more precision we lose, which is a big problem because our eyes can actually notice differences in color better in darker shades than lighter shades. And even additionally, on mobiles, you really want to use texture compression to save on bandwidth. And when you have the imprecise result on the right, and then texture compression on top of it, you're going to get an even more imprecise result. So this technique does not work, unfortunately. It will be cool because there was no performance loss doing it this way. But this gave us an idea of something else to try. What if instead of converting our texture to gamma 1.0, we actually convert it to gamma 2.0? The idea is that gamma 2.0 is actually much closer to 2.2, so the loss of precision will be minimal. But in the shader, when you want to raise it to the power of 2, you just multiply it by itself. And the multiply is much less expensive than a power. So in the shader, we just do that on every texture fetch. And when you're doing this, you also have to correct for the hardware zone correction at the very end of the shader. So don't forget to do the last line. At the very end, your color needs to be inverse corrected with the gamma that you're using. And that's pretty much how our PBR works. And we use that for our directional light. But we also want to have some other lights on the scene as well. We very quickly realized that for spells to feel awesome, they need to affect the environment at large without adding any additional visual noise to it. And the idea here is that we can use point lights in spells only to make them look better and to have them have a greater effect. So we started with 4-point lights because we thought you're not going to be able to have more spells on the screen at the same time. But that very quickly proved incorrect. Our artists corrected us very quickly on that. And we also thought that maybe it would be cool if we had some smaller scale lights in the environment to make it more dynamic. So we thought how to solve this, because calculating more than 4 lights for every pixel in the entire scene simply isn't possible from a performance standpoint, except on the very highest end of devices. So the first thing that we thought is, what if we use per object lights? That's a pretty old technique, but it's proven to work very well. Well, the issue is that on mobiles, we also have to watch out for CPU performance. And the draw calls cost a lot. So we batch all of our objects together. And that way, our entire floor, for example, is batched together. And we are only going to have 4 lights on the floor. And we want all of them to be visible there. So then we started doing some more research. And we thought, what if we actually tried forward plus? So if you're not familiar with this, this is a tiled lighting technique where the screen is separated into different tiles. And only the lights that affect pixels in one tile are actually calculated by that pixel. And if you actually try to do this on mobile, you may think that we're completely crazy. And we thought the same thing as well. Because for forward plus, you need compute shaders. And compute shaders are not supported very well on mobile devices. Even on the devices where they're supported, they can cause GPU stalls when being used. And we were already GPU bound, so adding a compute shader to the equation would make us even more GPU bound and lose performance. But we thought we have a very specific use case. Why don't we actually try to simplify forward plus? So the first thing that comes to mind when you're using forward plus is that you need a depth pre-pass. You need to know which objects are in front and behind the lights. But in our case, we don't actually have a lot of depth in our scene. we just have the wall at the end and usually nothing much behind that wall. So we thought we can actually remove the depth pre-pass totally. And that's actually very good for us because the only reason to actually use the compute shader is if you have to access the information from that texture where the depth pre-pass is stored. So now that we don't have to use the compute shader, we can actually do the light culling on the CPU. And since the CPU is not well suited to this purpose, GPU would be much faster, but we had a lot of CPU power remaining, so we could spin this off to another thread and do it that way. We decided to go with very coarse grain tiles, 64 by 64 pixels, so that we could save on some CPU performance. And since we're doing this on the CPU, we cannot get the exact areas of the lights. We have to approximate somehow. So we decided to approximate the lights with spheres. But we need all of this in screen space, and we need to somehow project these spheres into screen space. And when you're projecting a sphere, you're going to end up with an ellipsis probably, unless your camera is orthographic. But we figured that our perspective is not really that strong. So we figured that we can actually project these spheres into circles. And the idea is very simple. We project the spheres into circles like the camera is orthographic. We increase the radius by about 10 to 20%, depending how close to the edges of the screen that sphere is, so that we can correct for the perspective. And this actually worked great in our case, and is the version that ended up going into production for this. If you have a camera that has a very strong perspective, you can actually try another thing. It was an approach that we were considering, but decided against since the first thing that we tried with the spheres actually worked. You can actually project those spheres into an axis-aligned bounding box. This will cost more, and determining which tile is in the box is going to be more expensive than determining which tile is in a sphere. But it's not that bad, and it would still work. It would definitely work better than a compute shader. So, that was it for our lighting pretty much. And now we come to its counterpart. Shadows. The approach here is pretty standard. We have a dynamic shadow map for moving object and a static light map for the environment. The dynamic shadow map is pretty standard, but some mobile GPUs actually support hardware 4-tap filtering, PCF filtering, and we use that whenever possible because there's not a big performance impact to do it. On hardware that does not support this natively, we only sample the shadow map one time, because sampling it 4 times dropped our performance way too much. For the static shadows, we use a light map, as you can see on the floor with the shadows of the leaves. And this is, again, pretty standard, but here's where the cool bit starts. So our light map is using all 4 channels. The first 3 channels have the light map, the color information for all of the lights. But in the alpha channel, we actually store a static shadow map. The reason for that is that calculating how much something is in a shader is actually computationally expensive, and we're already computationally bound. So ideally, we would want to move that to the texture, which we did by putting it in its alpha channel. The reason why we need this information is so that we can nicely combine the shadows. Notice when the character moves into the light map area, how the shadows merge together. This is something that we wanted to achieve for our game because we have a lot of areas where characters and shadows would overlap. And this combining is done when rendering the floor, since the floor has information from both the dynamic light map and the static light map. And the exact formula of how you do this is shown here. It might not be logical on first go, but it's actually very simple. We simply interpolate between light color and shadow color, depending on the information in the static light map, static shadow map. The only thing that I didn't mention yet is the minimum function over there. It simply has a diffuse factor so that we could nicely blend between self-shadowing animations on the characters and the dynamic shadows we get from the dynamic shadow map. And this is pretty much it for our PBR rendering part. All of the secret sauce was in there. And now we can move on to the next part, and that is how we shade our VFX and our spells. So the goal of our game is for you to be a powerful wizard. And a powerful wizard needs to cast powerful spells. So spells absolutely need to look amazing, and that's why we invested a lot into our VFX. Now, VFX is usually the Achilles heel of mobile, since you're going to end up with a lot of overdraw, costing a lot of performance and stuff like that. And VFX pipelines for mobile look much different than VFX pipelines for PCs. First of all, you shouldn't use any post-processing because it's going to cost you a lot. VFX pipelines on PCs use a lot of post-processing. Secondly, on mobiles, particle systems are actually expensive. So you have to limit how many of them you have per spell. We usually have a limit of 2 per spell. So again, in this part, we also decided to go really old school. We decided to base our VFX system on sprite sheets. The cool thing about sprite sheets is that you can animate anything and it will look amazing. The downside is that sprite sheets consume a lot of memory, and most mobiles don't have a lot of free memory. So you will have to bake your sprite sheets at a lower frame rate than your game runs at. We had to bake them at around 10 to 15 FPS, depending on the sprite sheet, how big it was. And you will very quickly, or rather your players will very quickly notice when the game is running at 60 and all of the VFX is running at 15. So we decided to go with a technique to solve this, and it has several names. We decided to call it motion vectors, but it can be also found under the name of flow maps. The technique is very similar to PC motion vectors. The idea is that between the different sprites in this sheet, you want to know how much each pixel moved. And the picture on the left is the actual sprite sheet. The picture on the right is the motion vector sheet. The technique itself is that simple, but provides amazing results. The one on the right is obviously with motion vectors. You can see how much nicer it is. It actually looks like it's running at 60, while the one on the left looks like it's running at 5 frames per second. So, how to implement this? So first of all, there's a link over there with a detailed description of the article that gave us our inspiration. Our implementation is slightly different for performance reasons, but you can go with both and choose which one looks better for you. This is how the motion vector texture looks like. The red and green channels simply contain the delta UV coordinates of how the pixel will move into the next frame. The blue channel simply contains a scale factor for red and green channels to give us more precision when calculating UV coordinates. And the technique simply has 3 steps. We read the current frames pixel from the sprite sheet, and at the same UV coordinates, we read the motion vectors value. That way we know how much that pixel is going to be offset in the next frame. We determine those coordinates of where in the next frame we need to read that pixel. And we read both of those pixels and simply interpolate between them. This is actually the only technique that I wanted to share in this part, but it's the one that gave us the absolutely biggest visual improvement in our game when doing VFX. And as I said, it's that simple to implement. So let's go to the next part then, skinning. I promised a lot more units, and this is actually how an endgame scenario looks like. We can have as many as 40 units on the screen at the same time. And all of those units need to be animated, and all of them also need to be skinned. And we had huge performance problems with this, because we were using CPU skinning at the beginning, since we're using Unity, and that's actually the default. It doesn't support GPU skinning on mobile platforms yet. And CPU skinning for us with this many units was taking 2 full cores of performance. Besides some phones don't even have 2 full cores, so you will be dropping a lot of performance. But even on the phones that have 8 cores, you'll be heating them up much more since you're using 2 full cores more. And additionally, since all of those units need to be skinned, you have to upload a mesh for each one of them every frame to the GPU. And this is going to cause GPU stalls, killing your performance even further. So we decided that we really need to fix this, and that we should implement a GPU skinning technique that would be mobile friendly and that would solve our performance problems. And we had a couple of different requirements for this technique. First of all, it should never do GPU mesh uploads because those stalls were really bad. We have a lot of the same unit types, so ideally we want the technique to support instancing as well. And obviously it should be fast. This technique itself shouldn't be fast just for speed's sake. It should be fast so that we can use the performance that we save here to improve some other parts of our game. And over here, I think we tried 10 different things. I could talk about all of them for like an hour or maybe even more. But I'm going to tell you the last 2 things that we tried because they're usable in a lot of use cases and you could probably use them even today. So the first thing we called texture-based matrix palette GPU skinning. The idea is this. Our characters don't actually have complex blend trees. And every frame for every character, we're calculating the transformation matrix, the translation, rotation, and scale for every single one of its bones. But we didn't need to do that because we know well in advance of what those transformations are going to look like. So offline, while the game is being built, we could actually bake all of that data into textures. This is an example of one of those textures. So every row represents a different bone, and the bones are sampled at fixed time intervals. So every column is a different keyframe in time, which makes every pixel a transformation. So since a transformation matrix is 4 by 4, but it can be represented by a 3 by 4 matrix, we needed 12 floats. And for 12 floats, we had to use 3 textures to fit them all in. This is kind of a problem if you want to read those 3 textures in the vertex shader. On the good side, when we're using instancing, the only thing that we need to pass for instance data is 1 float, the U coordinate of the texture where we need to read the animation from. The problem here is that if you would create this texture at 60 FPS, it would consume a lot of memory. So ideally, you want to create it at a lower frame rate. But if you do that, to make your animations appear smooth, you need to interpolate. And that's kind of a problem when you have matrix separated into three different textures. So how would you do this in an ideal case? You would read from keyframes 3 and 4. You would read from all 3 textures at the same time, from the same coordinates. You would have to reconstruct those matrices. Then you would have to interpolate between those matrices. And you would have to do this for every vertex and for every bone that's influencing that vertex. So you end up with 6 texture reads per bone influence per vertex. And in our case, we had about 80,000 vertices doing this. So you can imagine that the performance wasn't actually that good. And this technique has some problems. It reads the textures 6 times. It has to use 3 different textures, consuming a lot of memory. And it has to do interpolation math between matrices. But it's not a total loss. You need to understand this technique to be able to understand the next one. And we call the next technique texture-based dual quaternion GPU skinning. Again, dual quaternions are a very complex topic, so if you want to find out more, you should follow this link. I'll just give you a brief description. The idea is that dual quaternions are a mathematical model where you can use 2 quaternions to represent a translation and a rotation put together. So they can be used instead of a translation and rotation from a matrix. An additional really cool thing here is that scale is actually not included in them. In a standard transformation matrix, the scale will be included together with the rotation. You cannot separate those. And when you're animating humanoid realistic characters, you usually don't need to scale your bones. So this means, at least for our use case, we could get rid of the third texture that only has scaling and only use it on the characters that actually need it. So we ended up doing 2 textures. This technique is already looking pretty good, but the biggest advantage is still coming up. So matrices separated into 3 textures cannot be easily linearly interpolated before putting them back together. But when you sample at close time intervals your transformations and convert them into quaternions, you can interpolate between those quaternions using spherical linear interpolation, and you'll get a completely correct result. But since they're so close together, just using linear interpolation is going to give you a 99% correct result, which is fine for this use case. And the really cool thing is, since the first quaternion is stored in the first texture, and the second quaternion is stored in the second texture, you can actually use the GPU hardware to your advantage. You can interpolate between those quaternions with a single texture read using bilinear filtering. This saves you a texture read and saves you all of the performance that you would use when doing linear interpolation. And we also found another advantage. Animations baked like this actually looked good, even with a low sampling rate. Much lower than we could do with matrices. Matrices had to be sampled at least 30 frames per second to look good. These ones could go 15 frames per second, even less for some of our animations. The only actual downside to this technique is that you have a problem when you want to blend different animations. You would have to read from your texture 2 times, and then in the shader you would have to manually interpolate between them. This is usually not a huge problem though, because you only should blend between animations when you're cross-fading or doing similar things, and you're not going to be cross-fading all of the time. Maybe only 10% of your units are going to be cross-fading at once. And you can switch to the more expensive variant of the shader that does this blending only then. So we're actually pretty happy with this technique, and we actually put it into production. And so far we have only been talking about mobiles, but the really cool thing about this technique is that it's actually really usable on PCs as well. Last October, we worked together with Unity to create a tech demo for their Unite Austin conference. They were working on improving CPU performance and multi-threading in the engine. So we wanted to create a demo that takes full advantage of that, and immediately we thought, why not create a massive battle with a bunch of units fighting each other? And we actually used this technique on a PC to animate all of those units separately. And I'm just going to show you a small part of that video. You can actually see the full video on YouTube, but the point is that we are running 100,000 units, and we were not GPU bound by skinning at all. We were actually CPU bound by all of the AI and pathfinding logic, since every unit was individual. Okay, so that's pretty much all for the different techniques that we wanted to show you. And let's talk about the last part now, actually optimizing your game. When we're doing optimizations for mobiles, it's very different than when we're doing them for PCs or consoles. For those 2 platforms, you only need to chase frame rate. But mobiles are actually battery and thermally limited as well. So it's very important to watch out how much your game heats up the user's phone and how much battery it drains. Because if you heat up the phone so much that the user cannot hold it, or you drain the entire battery within an hour, it's actually highly unlikely that the user will want to continue playing your game. So when we develop, we try to find a balance between having a good frame rate and also not heating or draining the battery too much. On some devices that can run at 60, we actually lower the frame rate to 30 on purpose so that we can prevent heating. First of all, when you're doing optimizations, you should always use graphical profilers. I don't really need to tell you that, and I'm not going to. I'm going to tell you what we actually used graphical profilers for in a kind of unexpected way. We actually use them to iterate on shaders fast. The picture on the right, for example, is a Adreno profiler, but this actually works with all of the modern GPU profilers for mobiles. The idea is that when you're first writing a shader, or maybe fixing a shader or whatever, you will not get the same result on your PC as you would on your phone. So the idea is, what if we could iterate on the shaders directly on the device? And profilers actually allow that. You can change this shader directly on the device and deploy it within seconds. And for us, this saved us massive amounts of time, literally weeks. And when you're actually optimizing, you should always be mindful of your shader instructions. This is the count for our full-featured PBR shader. It has about 250 instructions. The really cool thing here is that it separates them into full precision instructions and half precision instructions. Half precision instructions are much faster to calculate than full precision instructions, so you should always use them on mobiles. The problem is that most PCs don't actually support half precision, so you'll get surprises when you're deploying the shader from your PC to the device. And that's why it's so important to be able to quickly iterate. It's logical to use half precision instead of full precision. But the thing that is not logical is that you should never use fixed precision on mobiles. The thing is that mobiles actually kind of support fixed precision, but they usually don't have units for that. They either use half precision or full precision units, so you won't actually gain any performance, but you'll be losing precision. Even worse, converting between precisions on certain phones is actually cost you performance as well. So you should convert between them sparingly. And if you're using fixed, at some point you will need to raise it to half precision, and at that point you would lose performance. So it's better if you started with half precision anyway. The thing here that's interesting is no-op instructions. You can see that our shader has 37 no-op instructions. At least that's how Snapdragon Profiler calls them. This means that your shader, or rather your GPU, might stall for some reason while executing this shader. In our cases, we usually found that happens when you're bandwidth bound and trying to fetch from a lot of textures, if you use branching in your shaders, or if you're converting between precisions a lot. Decreasing the amount of no-op instructions can actually improve your performance without sacrificing any visual quality. So you should be always mindful when you're developing shaders to watch out for how many of no-op instructions you have and try to reduce them by playing around with your shader. No-op instructions can actually come from some weird places as well. I'm going to give you the weirdest example that we have encountered while developing this game. So, if you ever did matrix palette skinning, this is a pretty standard line that you would find anywhere when you're doing this. We have an uniform array of matrices, and we fetch two of them, weigh them depending on how much they're influencing the vertex, and we sum them together to get a complete transformation matrix for that vertex. You saw that our shader has 250 total instructions. When we added this to the shader, it went up to 500 instructions. And 250 of them were no-ops, like literally going from 37 to 250 no-ops. And our performance dropped like a rock, which was very weird since we didn't actually do anything wrong here. You would expect this to work. So we took a GPU profiler, started playing around with this a little bit, and we ended up with this code. It's actually completely equivalent functionally to the code above, but it actually has 70 no-ops less. And it ended up being 20% faster in total. Not just this part of the shade, but our entire game ended up being 20% faster. Like, the only thing we did here was to fetch from memory a little bit earlier than in the previous shader. That way we could let the GPU execute some other instructions while it was waiting for a fetch from memory, and that's why the number of no-ops was reduced. The GPU wasn't stalling as much. But we can reduce them even further, because we're waiting on memory. So if you actually put some instructions here in between those two lines that don't actually use any memory fetches, we could actually reduce no-ops to close to 0, which is what we did in the end. We included a bunch of different instructions in here, and the no-ops dropped even further. And our performance improved. That's pretty much it for optimizing. But let's talk about the other thing that I mentioned, heating and battery drain. This is a graph of one of our stress tests that we use for determining how the game behaves on a certain device. This is a Galaxy S5 actually, and it's a 1-minute test that runs in a loop. You can notice that the phone starts strong at 44 FPS, but within 5 minutes it actually drops down to 30, which is still okay-ish, not ideal, but okay. But after 15 minutes, it drops down to a completely unplayable 16 FPS. It then cools down a little bit, and after some time, it goes back up to 25 FPS. We really want our players to play the game for more than 15 minutes, so we knew that we had to solve this problem. You might also be thinking that I cherry-picked a really bad example, but that's not the case. I actually later took 4 random devices out of my drawer and tested all of them, and ended up with this. You can see that almost all of them are as bad. Some are even worse. This affects literally all of the mobile devices on the market, because the CPUs and GPUs are simply so powerful now, and the devices only have passive cooling. If they were running at full frequency the entire time, they would literally cook themselves. So you can solve this by dropping graphical quality, but it's really important to know how to test this, because if you keep testing your game while the device is cold, you're not going to be able to notice this. And the user will probably never have a cold device because they might be doing something else with their device before they play your game. So the process that we go through when we're trying to determine how much we should drop a graphical quality for a certain device is that we wait until the device goes into the stable state. In this case, it's when it goes to 25 FPS. Then we decide if we want to target 30 FPS or 60 FPS with this device. Since it's highly unlikely that we could target 60 FPS without it overheating, we decided to go with 30 FPS for this specific one. So we do that. And then we tweak our graphical quality, we turn off shader features and some other stuff, so that we get the FPS stable about 30% above our target. In this case, that means that we want our FPS to be at 40. And finally, we cap the frame rate to our target, to 30 FPS. This means that our game is capable of running at 40 FPS on this device, but we don't allow it to go over 30. The reason for that is that it actually has some free headroom between frames to drop its frequency and cool down a little bit. We are not actually using all of the resources the device has, so it won't heat up as much. And it also helps that if you have some frame rate spikes, it amortizes them a little bit, so the user will probably not notice them. This specifically is quite a long process, because you first have to heat up your device and then wait for it to go into stable state. For most devices, this takes between 15 minutes to half an hour. And there are over 10,000 Android devices out there. You won't be able to do it for all of them. So we decide on our graphical quality or the quality settings for the device, not per device type. but per the GPU that it actually has in it. That's information that's easily accessible. The information that's not as easily accessible is the frequency that the GPU runs at. Because you can have multiple devices with the same GPU, but some of them will be clocked lower, so they would heat up less. And it's really hard to know this, and it's really hard to have all of those devices at hand at the same time. So we actually use our analytics platform to track performance. The two most important things that we tracked are average FPS, so that we could find devices that have lower clocked GPUs than the ones that we actually tested in-house. But we also track battery drain. The reason for that is that because ideally, we would like to track heating. But tracking heating in consumers' devices is close to impossible. But we actually found that battery drain is strongly correlated with heating. And as a rule of thumb, we know that we shouldn't drain more than 40% of the user's battery on most devices. And if we don't go over 40%, it's highly unlikely they will ever overheat. This process can be very painful if you have to wait for a build of your game to be able to deploy new quality settings to the users. So another very important thing that we did here is to reduce iteration time of when we're changing quality settings. And we did that by distributing the settings whenever the user starts the game from our server. That way, as soon as we notice that the device is underperforming, and it's likely that we don't have the device in-house because there are 10,000 devices, unless it's a very popular flagship, we will not have it. So we change the settings, put them on a server, wait for an hour or two, it will get propagated to all of the players, and we can see how the game performs now. If it's performing over our target, then we're okay. If it's not, we iterate further. And that was actually it. So I would just, at the end, I would just like to do a short recap, not of the techniques that I showed you, because you have probably already remembered the techniques that you can use for a game, but of the way we actually do things. And important things that I hope that you got from this presentation. We usually start with generalized techniques, but as soon as we notice they're either a performance problem or that we need some other approach, we very quickly specialize them. And on mobiles which are performance constrained, this is totally worth it. Additionally, mobile graphics are lagging behind PCs about 5 to 10 years, depending on what area. So it's worth it to research old school PC techniques that are no longer used, because a lot of them will actually fit mobiles very well, such as the sprite sheet approach to VFX. And finally, you really need to be extremely mindful of heating, and you really need to test your game with a heated up device. You shouldn't do it with a cold one. Okay. Before I officially finish, at some point you will get a survey. Please fill it in, because I would really like to hear your feedback on this talk. And that was pretty much all from me, so thank you very much. And are there any questions?
When you did your thermal throttling testing, did you do that on AC power or strictly on battery?
Strictly on battery. If you do it on AC power, the device will overheat immediately, so you won't be able to get correct results. So for that one specifically, we developed a server that runs together with the game, and we get the data via Wi-Fi.
I was wondering about that. Thanks.
Okay. Anyone else? Don't be shy.
Hi. You said your technology is scalable up to iPhone 4S.
Yes.
And as far as I know, you can't read textures in Vertex shader.
Yes.
on this device?
Yes, so about 20% of the devices that our game is played on don't use the GPU skinning because we simply cannot run it on them. The problem is actually pretty severe because according to OpenGL specification, you have to support that in your hardware. But also according to specification, you don't actually have to provide any texturing units to read those textures. So we actually blacklist some devices. We usually blacklist iPhone 4S, as you said, and Mali 400 devices. Everything else usually works.
Thanks.
No problem. Oh, I guess that's it. Thank you, guys.